Good morning everyone. Good afternoon. Thank you for the possibility to present part of our results, which was obtained on the nickel oxide cobalt platinum 3 layers. This work was done with strong collaboration with Institute of Molecular Physics in Polish Academy of Science. The outline of the talk is like the following. First will be some motivation, and then after our earlier studies on similar systems, and then new results which was obtained, and finally the conclusions. The interfaces have a big influence on magnetic properties in ultra-thin films. So changes on interfaces, it is possible to modify the magnetic anisotropy in ultra-thin films, like it is presented here, where we have cobalt wedges, which is covered partly by gold or silver, and what is visible here, that depending on the coverage, spin orientation transition is for different cobalt thicknesses. So the out-of-plane regions is visible in different ranges of cobalt wedges, and this is guided mainly on the different contribution to the anisotropy of surface and volume. If you are talking about the interfaces, also in the last years is interesting and intensively studies new interactions like Dzyaloshinskii-Moriya interactions, which is present when we have some breaking symmetry. So we have asymmetric interfaces. This interactions is very interesting because it allows us to stabilize submicrometer domain sizes, magnetic domain sizes, which have some chirality. It is like bubble or stimulants, like it is visible, for example here. Earlier studies, as I said, it was done with collaboration with Institute of Molecular Physics. Layers which was done by sputtering techniques, and we start to measure from the cobalt wedges surrounded by two golds. So as I said, in such kind of systems, when we have cobalt wedges, we have some transition, we have out of plane, in plane, and some transition. And the question was, what, for example, change when we put instead of gold some other materials like nickel oxide, which is antiferromagnet, and it turns out that it is possible to change the presence, or when out-of-plane magnetic anisotropy is visible, so the ranges of the thicknesses is wider, and also spin orientation is for higher cobalt thicknesses. So nickel oxide enhance the normalized remanence and also magnetic anisotropy in such kind of layers. If nickel oxide is antiferromagnet, so it has some null temperature. We can say also about null temperature, and there is some feature that depending on the composition of nickel oxide and cobalt oxide, it is possible to modify null temperature. So if we are talking about the null temperature, and this temperature is not so big, it is possible in these layers, such kind of layers, to induce some thermal changes, as it is visible here on the same structure, that using temperature it is possible to induce spin orientation transition from out of plane to in plane, and additionally it is possible to demagnetize the sample, creating some demagnetized structure, including bubble-like domains. So goal in these studies was, let's use instead of gold, platinum coverage, and put the cobalt layers on nickel oxide layers. Why platinum as a coverage? Because it is known that it might expect that platinum has bigger Dzyaloshinskii-Moriya interaction then, for example, gold as is visible on this images. Why oxide? Oxide is interesting layer because it may have also DMI, exchange bias, or electric field effect. This DMI is quite big values, and using nickel oxide or oxide layers, it is possible to do some electric field driven experiments. Techniques which we used in the studies is magneto-optical polar magneto-optical Kerr effects, like is presented here. Two configuration, one with the field was perpendicular to the sample plane, but also to anisotropy we use field which was we use crossed field. We have field perpendicular and in the sample plane. Also we use some magneto-optical microscopy with polar and longitudinal configuration, and also brilliant light scattering spectrometry with backscattering geometry. So this is the sample which was measured. So we have nickel oxide as a buffer, cobalt wedges, and platinum as a coverage. So this is the remnant image of our sample. So one can see that we have white region when we have out of plane magnetic anisotropy, then we have in plane. So we observe transition from out of plane to in plane. The transition is somewhere around 1.5 nanometers, and also it is nicely visible when we have on the PMOG and LMOG hysteresis loop. This transition also visible. Then we have transition from out of plane to in plane, and from out of plane to in plane. LMOG also confirmed that we have some in plane anisotropy. If we have hysteresis loop, there might be described by such parameters like coercivity, remanence or maximal value of the rotation or ellipticity, and also some saturation field which is equal to the magnetic anisotropy field. When we, for example, plot such kind of dependencies, it's also nice visible this transition from out of plane to in plane. And additionally, what was observed here, that we have quite a big value of coercivity field. Also, what is interesting here, the measurement or analysis of the magnetic anisotropy, which have quite big values. As I mentioned, the magnetic anisotropy was measured using a crossed magnetic field. One field was perpendicular, second was in the sample plane, and using this field it was possible to measure changes of the MZ component of magnetization as a function of in-plane field. And this is the example. This is the exemplary curves for three different thicknesses of the cobalt. And also here this graph presents effective anisotropy multiplied by thickness of the cobalt as a function of cobalt thickness. So we can see quite nice linear dependence. So also it confirms that we have some transition from out of plane to in plane with spin orientation around 1.5 nanometers. So using this value and these dependencies, it's also possible to estimate volume and surface contribution to anisotropy, and this value is quite big in relation, for example, to similar systems with nickel oxide when the gold, for example, was used. When we compare it, so one can observe that we have quite big difference, especially on the surface anisotropy, which guides the magnetic properties or magnetic anisotropy in our systems. So this is one of the interesting results. So what's happened, for example, or how they looks like magnetic domain structure. So two studies the magnetic domain structure, or to have a look if we have some asymmetry on magnetic domain structure. So we focus on these places. So where the unfortunately coercivity is quite big, because it is 1.5 0.1 Tesla, and applying magnetic 2 pulses of the field perpendicular and in the sample plane. Of course, AX was applied perpendicularly to the wedges, and when we have a look on the magnetic domain structure behavior, it turns out that we have nice asymmetry of the applied magnetic field. So it may confirm that we have some Dzyaloshinskii-Moriya in our sample. When we have a look on the cross, for example, in this on one of this domain, one can observe or deduce or schematically shown how the magnetization change, and it allows us say or conclude that we have some asymmetric domain wall propagation with some anti-clockwise chirality. So it proves that we have some Dzyaloshinskii-Moriya in our sample. So then, to check it or say something more, some brilliant light scattering spectrometry studies was done, as I said, on the backscattering geometry, and this is the example of the BLS spectra for the one of the thicknesses 1.35 nanometers for one K vector, and also for two spectra measured in field applied plus and minus 0.5 Tesla. So this is the spectra. So this is stocks and anti-stocks, and what we can see here that we have significant frequency difference between stocks and anti-stocks, and this differences is related by this formula with the effective Dzyaloshinskii-Moriya. So to say something more about the d-effective and dependences of as a K vector, we plotted for two value of magnetic fields, like it is presented here, and also as a function of K vector. So one can observe and deduce linear dependence of this df, and also it is possible to conclude the effective, for example, for these two thicknesses presented here, like it is 1.35, 1.1 millijoule per square. So if we have the effective, so using the formula, it is possible to estimate interfacial DMI as a function of d. So it is possible to plot it, and it turns out that this value, this estimated value, is around plus 2 picojoule per meter. It is one of the bigger values of the DS. And when we compare it with similar system with nickel oxide, for example, with gold, this value is higher. And even when we compare it with one of the last published paper with the same system, however with opposite configuration, platinum and nickel oxide, one can say that this value is higher, and also the sign is different in our cases. So basing also on the results in this work, it was also possible to deduce and plot additional information, obtain additional information like estimation of the or changes interfacial ds as a function of amount of any nickel oxide layer. So it turns out that this dependency is quite linear. So it is quite nice. Dependencies. So concluding, so using nickel oxide, it is possible to enhance magnetic anisotropy in our system with big values of surface contribution. It is possible in our system to observe asymmetric bubble domain expansion due to Dzyaloshinskii-Moriya interaction. It is also to visible significant value of interfacial DMI, and also linear behavior between this amount of nickel oxide and interfacial DMI. So thank you for your attention.